All right, y'all, so we're going to be looking at example number 3 from our notes. This says the angular velocity of the rear wheel of a stationary exercise bike is 4.00 radians per second at a time t equals 0, and its angular acceleration is constant and equal to 2.00 radians per second squared. A particular spoke coincides with the x-axis at time t0 as shown in the figure. So we see right here, there's a spoke that is even with the x-axis at this point, and then it's going to be rotating around and around. Okay, so there we go. That spoke is at time equals 0. The question is, what angle does this spoke make with the x-axis at time 3 seconds? All right, now I want you to take just a minute before you jump into this question. I want you to recognize that we have been given an angular velocity, right? Radians per second. We have been given an angular acceleration, which is radians per second. And I've been asked for the angle, which is the angular displacement or the distance traveled around the circle, all right? Now, if you were given a question that had velocity, acceleration, and distance or displacement, what would you do? Hopefully you're thinking, well, I would use kinematics. Yes, kinematics. So what we want to do is the same thing that we did back in the day when we did kinematics, is we're going to make a table and we're going to write down the information that we have, right? Do we have the initial position? Do we have the final position? Do we have the initial velocity? Do we have the final velocity? Do we have the acceleration? And do we have the time? Notice that it's exactly the same as before, except we're using the rotational quantities instead of the linear ones. So we can say that we start at 0, right? That's what it says, the particular spoke at the x-axis at time 0. So my initial position is 0. Okay, it does say the angular velocity is 4 radians per second at time 0. So that's my initial speed here. So 4.00 radians per second. Remember, in order to use kinematics, any of our kinematics equations, we do need it to be radians per second. It can't be cycles per second or degrees per second. It needs to be radians. They give me the angular acceleration, which is 2 radians per second squared. So I can go 2.00 radians per second squared. All right? And then they do give me the time, which is 3.00 seconds. Okay? The question is asking for the angle, or what is my angular displacement. So this right here is what I'm looking for. You'll notice that just like back when we did kinematics, there's one variable that we don't have and that we don't care about. So therefore, make sure to pick the kinematics equation that doesn't have that in it. We need this, and we have all the other information. So when I look at my kinematics equations here, okay, I'm going to look. I've got this one, and I've got this one. And remember that we actually have this guy right here as well, which would be omega squared, omega initial squared, plus 2 alpha theta minus theta naught. Okay? Now, in this situation, we want the one that does not have omega in it. So this one would have that omega right here. This kinematics has the omega right there. And so I'm going to choose this equation. I'm going to choose the theta equals theta naught plus omega naught t plus 1/2 alpha t squared, because that's the only one that doesn't have the one variable that I don't have and don't care about. And so now I should just be able to put it into my kinematics equation. So that final angle, that final distance, equals the initial position, which is 0, plus the initial speed, which was 4, times the time, which is 3 seconds, plus 1/2 times the acceleration, which is 2 seconds, times the time again squared, which is 3 squared. And so now I just plug those numbers in. I go 4 times 3, sorry, you can't see, 4 times 3 plus 1/2, which is 0.5, times 2 times 3 squared. And I push enter and I get 21. All right, so theta equals 21. Now, because I used radians and radians per second and radians per second squared, the angle will be in radians. Now, the question, of course, is what angle does this spoke make with the x-axis? Well, technically you could say 21 radians because 21 radians would just go around the circle several times before we finally passed it and got to an angle. Now, if you want the angle between 0 and 2 pi, then the way to do that is to find out how many circles there are. And so we're going to take that and divide it by 2 pi to find out how many times we go all the way around. So if we go 21 divided by 2 pi, then we get 3.3422 like that. So I'd get 3 full cycles, and then I'd get this many partial cycles. Okay, so what I'm going to do is I'm going to subtract off the full cycles because I knew I made 3 complete cycles, right? So that goes 1, 2, 3. And now I'm back here, and now I need to do 0.3422 more cycles. Okay, so I need to do 0.34225 new cycles. And in order to turn that into radians to get the angle, I'm going to multiply by 2 pi radians per cycle. And so we just take that number and we multiply by 2 pi. And we get 2.15. So the answer is that the angle, if I want something between 0 and 2 pi, the angle would be 2.15 radians. And that would be exactly how far I've gone. Now, that's a little less than pi, right? So it's less than 2 pi. It's between 0 and 2 pi. So it would be somewhere over in this area right here. Okay? Awesome. That's part A. Now, part B is, what is the wheel's angular velocity at this time? Okay, well, angular velocity at this time, well, that is now asking me to find this guy right here. Now, I know that the theta now is, I'm going to put this is going to go here because that's going to be how far it's rotated and rotated and rotated all in the correct, I guess it's this direction because it's spinning this direction. Okay, so that 21 radians can go into that theta right there. And so now I just need to make sure to find the angular velocity. Now I'm solving for that omega. So I go back to my equation sheet, and I can use any of the equations that have omega. This one right here definitely has omega in it. The omega equals omega naught plus AT. I could also use this one with the omega squared equals omega naught squared plus 2 alpha theta minus theta naught. But you're probably saying, no, Mr. Baldwin, don't do that, because you recognize that this one is easier, so this is the one that we're going to use. We're going to use the omega equals omega naught plus alpha t. My final speed, that's what I'm looking for, so that's just omega. The initial speed was that 4 radians per second, so omega equals 4 plus the alpha, which is 2, times the time, which is 3 seconds. So I've got radians per second squared, and seconds. And I put all that together, and I get 4 plus 6, so omega equals 10 radians per second. Just like before, if you use SI units, then your answer will come out in SI units. And so you'll notice that anytime I did anything with the rotational, the angular displacement, the angular speed, angular acceleration, any of that, I always put it in radians per second squared, because the radians is going to allow us to do the kinematics and leave us with an answer in SI units. All right, so there you go. We've completed example number 3, and hopefully that helps you see a little bit more how we will connect what we've been doing with the rotational information and the rotational terminology to a situation that was the old kinematics. All right, so there you go.